So let's do a quick example on how this thing is actually used in practice. You could consider a situation where both walls are stationary and there's fluid entering in one direction from one end and coming out the other end. It turns out, so this is for a problem, you can consider this to be a given, there is a velocity profile. So there's a velocity profile that looks quadratic in nature. So recall that we said that the velocity is always 0 at the wall for a viscous fluid. So what we are saying is that the velocity now in this parallel plate channel is given by u of y is equal to 1 minus y square over L square, where the height of this channel is given by 2L. So if that is the velocity, and let's multiply that by some u max, which corresponds to the center line velocity. So that tells me that my velocity profile has a maximum at the center line, which is where y starts. So for y equals 0, my velocity is u max, and at y equals plus or minus L, this term essentially is 1, so 1 minus 1 gives you 0, so the velocity is 0 at the wall. So this is a velocity profile that is actually encountered in practice, and the question is, so if this is given, the question is find the distribution of shear stress in the channel. And knowing the distribution of shear stress, we can find the forces on the walls, and so that is the practical implication of this. Just by knowing the velocity profile, we can calculate the shear stresses everywhere in the fluid, and the shear stress at the wall is the shear stress acting on the fluid, and because action and reaction are equal and opposite, that is also the shear stress acting on the walls, and therefore knowing this velocity profile tells us what forces are acting on solid surfaces which are exposed to the fluid. So the solution is pretty straightforward. We are essentially going to just use the definition of shear stress as related to viscosity. So if this fluid has a viscosity mu, a dynamic viscosity mu, the shear stress is given by mu times du dy, and therefore the stress tau of y is given by mu times d by dy of u max times 1 minus y square over L square, and so that gives you minus 2 mu u max y over L square. So if I were to plot that, what it tells me is that the shear stress is linear when my velocity profile is quadratic. It's 1 order of magnitude less. So my shear stress, according to this, would go as that. So that is my distribution of shear stress. And we'll see in class, in an example, that we can use the same idea in a cylindrical geometry to actually measure viscosity. So we can look at this equation in two ways. One is knowing the viscosity and the velocity profile, I could calculate my forces everywhere. Or alternately, we just defined a viscosity and we really don't know how we would measure it. We know it's a measure of deformability, but I'd like to know how it varies from liquid to liquid or gas to gas. And one way of measuring that is to actually use this definition where I apply a known shear and I measure my velocity profile and I back out my viscosity. We'll do that in class.